the morning session. And so this time it's my pleasure to introduce Tomoyuki Arakawa. We'll be talking about 4D, 2D duality, and VOA theory.
Thank you very much for the introduction. So Vertex Operator algebra, Vertex algebra was introduced by Borges as algebraic framework for a two-dimensional conformal field theory, like two-dimensional chiral conformal field theory. So this is something a two-dimensional thing. However, a recent discovery which actually goes back to Nakajima-san's work. In 1904, where he defined the action of affine Katsumori algebra on the homologous group of certain instanton moduli spaces. And recent discovery is that the VOA appear in higher dimensional quantum field theory. So higher means the dimension of this quantum field theory has a dimension equal or greater than 3. So this is something we don't expect from the definition or from the origin. But this already heard in this school in Professor Gukov's talk yesterday, and also Nakajima's talk. Kind of a big trend now. And so in my talks, I'll explain one of such a discovery, which is different from Gukov's talks and Nakajima-san's talk. So it's a correspondence discovered by Beam, Lemos, Piendo, Pilas, Rastri, and Van Ries quite recently. So what they did was they defined a map or a functor from the category of four-dimensional n equals to 2 superconformal field theories, whatever it is, to the category of a Vertex Operator algebras. So they denote it by this functor by chi, but chi is often used in mathematics, so let me use the notation V for this map. And this map was designed to do the following. So there's an important invariance of this four-dimensional theory called a Shear index. Which is some kind of a Q series. And so this map was designed to produce this Shear index by considering the character of the corresponding Vertex Operator algebra. So this is a vector space, it's a graded vector space. And so you consider a corresponding normalized character. which is the sum of the following. So dimension of VD, QD minus C over 24. So this in theories was this vertex operator algebra is a categorification of the sugar index. And so this map has several properties. And one of the property is that there's a central charge for this vertex operator algebra. And let me denote this central charge C2D. And this central charge of vertex operator algebra is the minus 12 of central charge of the four-dimensional theory. So there's a notion of central charge for the four-dimensional theory. And because central charge takes non-negative value for unitary theory, which is a case for the physical theory. So this means if you start with a unitary theory in four-dimensional, you end up as a non-unitary theory for the two-dimensional. So this means that the vertex operator algebra obtained by 4D theory is never unitary. And so this in particular means that this map is not surjective. So unitary VOA do not come from the four-dimensional theory. And another thing, so this map is defined by certain dimensional reduction. So we go back from four-dimensional theory to two-dimensional theory. So this is done basically restricting the theory to the two-dimensional plane. So you might think this loses a lot of information of the four-dimensional theory, but in fact, people believe that this map is so this is expected to be injective. And this is true in examples. So in other words, the vertex operator algebra is a complete invariant of the four-dimensional theory. So this is something extraordinary because this four-dimensional theory, I don't explain what it is, but this is a very extremely rich theory, but not mathematically defined. So unfortunately, for the moment, quantum field theory, which has a dimension greater than 2, is not mathematically defined. So this one is not defined either. But this is something very concrete and mathematical. This is math. No, I don't think so. So this is mathematical. So we have, so we should have in this category as a full subcategory, which correspond to this very rich four-dimensional theory. And so this map was originally designed to give a Schur index, but it turned out this does much more, and so there is a conjecture by Bean and Rusty which says the following. So, as I said, this four-dimensional theory is a very rich theory, and it has many. It creates many mathematical invariants, and one of it is so-called a Higgs branch, which is so this is a Higgs branch of the four-dimensional theory, which is a hyperkähler cone. So this is certain geometric invariant of the four-dimensional theory. And the statement is that this Higgs branch should be isomorphic to the associated variety of the corresponding vertex operator algebra. So this I will define in a minute, associated variety of vertex operator algebra. For any four-dimensional n equals to 2 superconfirmed fields. So this does not only give the Schur index, it also gives Higgs branch by considering associated variety. So we suppose to have this nice commutative diagram. And this Higgs branch so this is a hyperkähler cone. So in particular, it's a symplectic variety. And this Higgs branch is often, in most cases, has so-called symplectic singularity. In most cases. So Terry said yesterday that the category theory is a group theory for the 21st century. And symplectic singularity is a Lie algebra for 21st century, according to Ogonkov. So the corresponding vertex algebra can be considered as a chiral quantization of this symplectic singularity, which is something for the 21st century. So this will be very interesting. And maybe I should also explain connection with Coulomb branches of the three-dimensional gauge theory, because it's kind of becoming a big subject. So if you have a four-dimensional n equals to 2 superconfirmed field theory, you can get a three-dimensional theory, again by dimensional reduction by so-called S1 compactification. And then it's known that the Higgs branch remains the same. And if you go to three-dimensional theory, there's a duality called 3D mirror symmetry. And you can identify this Coulomb branch, Higgs branch with Coulomb branch of the dual theory. This is 3D mirror symmetry. And when this mirror theory is a quiver gauge theory, this Coulomb branch was recently defined by Braverman and Finkelberg and Nakajima. Braverman, Finkelberg, and Nakajima. And you can think the corresponding VOA as affinization of the Coulomb branches. And you'll see later in my lecture such an example. So we get many interesting Vertex Operator algebra out of this four-dimensional theory. And we'd like to understand their properties. Okay, so any questions so far? I didn't state any mathematical statement yet, but so now I'd like to explain associated variety because it connects VOA with this interesting geometric object via beam-Russell conjecture. And it also gives a very powerful tool in the study of a vertex algebra. So let me explain associated variety and applications. So the model here is the associated, there's a notion of associated varieties for the primitive ideas in UG. So if you are familiar with such a notion, you find many similarities, but I will not talk about so much because I think this connection is explained in Anne's short course in April. So let me directly start with a vertex operator algebra. So V is a vertex operator algebra. So in my lecture, I loosely use vertex operator algebra just to mean a conformal vertex algebra. So so if you have an element, you have corresponding quantum field. I often sometimes write as AG or YAG and expand slightly different way from EG's. So he didn't put this bracket here, but I put bracket following Victor's notation. And I don't know how much audience know about vertex operator algebras, but there's a notion of a strong generators. So strong generator means that this V is spanned by these monomials. Vacuum where Ni, all Ni is non-negative. So if you use quantum state field corresponding to this correspond to state field correspondence, the corresponding fields are of the form like this. So normally ordered product of derivation of these strong generators. So I fix some strong generator, and then you can define some filtration of this vertex operator algebra defined by Haishan Lee. And the definition is very simple. You just count number of the derivation here. So if P of V is a span of these monomials with sum of Ni is equal or greater than P. So this space that spanned by monomial which has at least P derivations. Then this gives us a decreasing filtration of the vertex operator algebra. So this is called Lee's canonical filtration. And intersection is zero in the cases we consider. So namely, if V is positive, non-negatively graded, non-negatively graded. And so this has some compatible with the product algebra structure of the vertex algebra in the following sense. So if you multiply nth product from Fp to element of Fqv, this sits inside Fp plus Q minus n minus 1 of V. And if actually it goes to one more step down, if n is non-negative. So this is for all n. And from this, you find that the associated gradient is naturally a Poisson vertex algebra. So this is associated gradient, which is isomorphic to V itself as a vector space. So this is a Poisson vertex algebra. I hope you know Poisson vertex algebra, but if you don't know, you just think as just a commutative algebra. It's a commutative algebra with some extra structure. And the product of this commutative algebra is defined by sigma p applied to sigma q. A is sigma p plus q, A minus 1b, where sigma p is the symbol map. So sends fp to fp fp plus 1v. So a minus, so when n is minus 1, this is just fp plus q. So this defines the element of fp plus q. So just take a symbol of this element. And this gives this space a structure of commutative algebra. And also there's a Poisson-like structure. So you have nth product for non-negative n. So this is defined by fp plus q. So you consider a, n, b, which sits in here. So we take symbol in here for non-negative n. So I will not use too much structure as Poisson, but as, let's view this as a commutative algebra. So this is a very big commutative algebra. But if you look at the definition, we have this space, which is closed under this product. Because if both p and q are 0, p plus q are 0 also. So this is a subring of this commutative algebra, which denoted by RV. And in fact, this is not only a commutative algebra, but is a Poisson algebra. So I write again the commutative algebra structure. So commutative algebra structure is given by a minus 1 product. And Poisson bracket is given by sigma 0 a 0 of sigma 0 b, which is by definition sigma 0 a 0 b. And this Poisson algebra was introduced earlier by Zhu, and it's called Zhu's Shitsu algebra. So what Haishan Li did was he defined Poisson vertex algebra structure on this associated gradient and show that the Zhu-Shitsu algebra can be obtained by restricting the Poisson vertex algebra structure on this subspace. And and this Poisson algebra is in my talk for all vertex algebra. This is finitely generated a Poisson algebra. This is the same as it has generate a finite many number of finite strong generators. So what Haishan Li showed that this associated gradient is generated by this subalgebra RV as a differential algebra. So I forgot one thing. So it's a Poisson. I have to give. I forgot to. Maybe I should. Sorry. This is Poisson algebra is in particular a differential algebra. So differential algebra is nothing but the unitary, a commutative algebra with a derivation. And the derivation for this is defined by this translation operator, which is defined like this, TA. This is just L minus. So this T is a derivation of the Poisson vertex algebra. And so the statement is this group whole space is generated by this Zhu-Shitsu algebra. Now, because this RV is a commutative Poisson algebra, it makes sense to consider corresponding spectrum. So, and the corresponding spectrum is the associated variety of the vertex algebra. So this is associated scheme of V, but mostly we only interested in the of this scheme as topological space, so it's convenient to consider corresponding a reduced scheme, so which we call associated variety. So this should give us the Higgs branch if vertex operator algebra comes from the 4D theory. Now, so in Terry's talk, he said the nicest vertex operator algebra are those which are rational and Shitsu-cofinite. And Shitsu-cofinite is defined using this associated variety. So V is called least. So I prefer to call it least, but it's the same thing as Shitsu-cofinite. If a dimension of this associated variety is just 0. And so you might look this condition somewhat artificial, but you can show that V is least if and only if the spectrum dimension of a spectrum of this whole space group V is 0 by using this least theorem. And so this least condition is a natural finiteness condition of the vertex operator algebra. And so let me assume V is non-negative graded, but it might grade it by half integer, not by integers. And the dimension of each homogeneous space is finite, and top space is one-dimensional, unless otherwise stated. There might appear some exception, but let me assume this for the moment. Then this least condition, so then this associated variety is conical, because Zuzic's algebra is graded. So it has a contracting sister action. So V is least if and only if this associated variety is just a point. And as Terry said, these vertex operator algebra are very nice. So I think he is going to explain how nice they are, so I will not say too much things about them. I just want to give some names who showed these vertex operators are very nice. So Zhu and Abe. So Zhu showed that I just let Terry to explain this, so I will explain. So these people show that these vertex operator algebra are very nice. Miyamoto. So among these statements, Huan showed if this vertex operator algebra is in addition rational, which means every representation is completely reducible, then a corresponding module category of the vertex operator algebra has a structure of a modular tensor category. And this is a very nice result. So we all know that the least vertex operator algebra is very nice, but if you want to study vertex operator algebra coming from 4-dimensional, so we cannot assume that the vertex operator algebra is least, because if V is coming from some 4-dimensional theory, then associated variety is supposed to be, if you believe Beam-Russell conjecture, isomorphic to a Higgs branch of the 4D theory, which has a positive dimension in general. So this has positive dimension in general. There are some cases when a Higgs branch are points, but this is not the whole case. There are many more interesting cases which of non-trivial Higgs branches. So somehow we need to extend what these people did to non-least vertex operator algebras. Excuse me. Yes, so what we can do? So by definition, this associated variety is a Poisson variety. So it has a stratification by a smooth analytic Poisson manifold. I. So Xi a smooth analytic Poisson variety. So first you remove singularity from this Poisson variety. And then you remove singularity from the singular part of the associated variety. And you continue. And you get such a stratification. So, particular symplectic leaves in the Poisson variety makes sense. And so it's the same for the Higgs branch. And by physical consideration, Higgs branch of the four-dimensional theory expected should, maybe I should say should, have a finitely many symplectic leaves. And this finiteness condition, so this is certain finiteness condition. So it makes sense to consider a vertex operator algebra that satisfies such a condition. So we call vertex operator algebra a quasi-Lie if the associated variety has finitely many symplectic leaves. So by this observation, if vertex operator comes from 4D series, it should be quasi-Lie. So what we can say about quasi-Lie vertex operators? I should say that this notion is, of course, generalization of a Lie property, because if V is Lie, then this means associated variety is just a point. So point is a trivial symplectic leaf. So this means V is quasi-Lie. So this notion generalizes this Lie condition. And also, what we can say, if V is quasi-Lie, you can say that the image of conformal vector, so this conformal vector of a stress tensor, is nilpotent in Zuzit's algebra. So this is not, so this you can show. You can show that if V is quasi-Lie, then image of conformal vector is nilpotent. And this finiteness condition implies by a result of Brown and Gordon that if V is quasi-Lie, then symplectic leaves which has finitely many in XV are algebraic. So simply leaves defined in that way are not necessarily algebraic, but if it's finite, then it's guaranteed to be algebraic. But the most important result of this finiteness of symplectic leaves are due to Eitingoff and Shedler. I think it's around 10. And they showed the following. If suppose R, so let R Poisson algebra, and consider corresponding spectrum, which is a Poisson variety. So suppose this has finitely many symplectic leaves. Then dimension of this quotient space is finite. So this is zeroth cohomology, zeroth Poisson homology of this Poisson algebra. So this is something you are interested in, and what they show that this is a finite dimension if this finiteness condition holds. Yeah.
I might have asked you several times this, but is there a counterexample for the converse of this?
I don't think I don't know. I think I asked Pavel, but I don't remember his answer.
And here, R needs to be reduced, or could it be anything?
Could be anything, but it's just finitely generated.
And just the last one thing, do you know if it implies anything about the higher Poisson homology?
That was questioned in their paper, but no results. Okay, so this result is very important because we get the following immediate corollary if we know the Zoo's result. So this theorem combined with Zoo's argument, we have the following statement. So theorem. So suppose V is quasi-Lie. The first statement is that the number of simple ordinary representation of V. So ordinary representation are those representations where a character makes sense. So those representations which have finite dimensional homogeneous L0 eigenspace. So this number is finite. So this is up to isomorphism. This is finite one statement. And another statement is that if M is a simple ordinary, so there are finitely many simple ordinary representation. So let's say My, simple ordinary representation. Then character makes sense. By definition of ordinary representation. And the statement is that this converges to a holomorphic function on the upper half plane, where Q equals to E to 2 pi I, tau as usual. And if you consider a span of these characters, which are a holomorphic function on the upper half plane, it is contained in a solution space of some modular linear differential equation. So modular linear differential equation. So I will not explain what is modular linear differential equation. It's just a differential equation which modular form satisfies. And the consequence is that the solution space, there's a natural action of a modular group on this subspace. So it's contained in a finite dimensional representation of the modular group. So what this saying is that so in particular, if you believe the beam rastri conjecture, then the Chiral index of 4D n equals to SCFT. So this is a character of V, which is a simple ordinary. Maybe we have to assume simple. Which is V is some Mi. So it's contained in a finite dimensional representation modular group. So this implies some modularity has some kind of modularity. How to say, modularity property. Which I think only way to see modularity property of the Chiral index of the four-dimensional for the moment. Okay, so I have 30 minutes more. So maybe I should.
I have a question.
Oh, where?
I have a question. So is there a relation between the dimensions of Poisson homology and the numbers of simple ordinary representations?
Dimension of what?
Dimension of Poisson homology. You said this is finite dimensional by adding of Chiral.
And number of modules.
Simple order.
So
some bound or something like that.
yeah, so yeah, I was asked the same question by some physicists, and I remember the conclusion was positive for that answer, but I forgot the details. So it's not directly.
The rational case is less, and it's in general. This Poisson homology bounds the kind of homology in degree 0.
Right, yeah. So
But only in rational case, do you know the
Yeah, only in the rational
characters?
case.
So this need not be equal. So in Zoo's case, the space is this is exactly the same. So and this is the same as a dimension of a conformal block on an elliptic curve, which is basically the same as this homology space. So, but in general, this is smaller. And does this answer to your question, Nakajima-sensei?
Yes. Thank you.
Yeah, so I forgot to say, in Zoo's situation, he showed that it is exactly equal. But for our case, in general, this is can be smaller. So this statement is not as long as strong as statement as Zoo's one, but still gives some nice description. So maybe I should explain how we use this result of Oettinger von Schedler, which I think I already explained just now, but maybe I should explain for the first. So maybe outline of proof. So number of a simple ordinary representation is the same as number of a simple finite dimensional representation of Zoo's algebra by Zoo's correspondence. So the Zoo's correspondence gives a one-to-one correspondence between simple positive energy representation and the simple Zoo V modules. An ordinary representation means that it corresponds to a finite dimensional representation of Zoo's algebra. And this number is equal, the smaller than a dimension of Zoo of V divided by a commutator. And this is equal smaller than a GUR. So this Zoo's algebra is naturally filtered, so you can consider corresponding associated graded. And so this equal smaller than the dimension of GUR. Yeah. So I have to, and then I use the fact that there is a surjection from Zoo's algebra to GUR of Zoo's algebra. So this shows that this is equal than smaller than RV. This is Poisson bracket, sorry. And this is finite dimensional by Oettinger and Schedler. And for the second statement, so I already explained what Zhu showed to show the inclusion, that he only used the finite dimensionality of the conformal block. So dimension of the conformal block on the elliptic curve so it's a one-point function. And it's very easy to see that this is equal and smaller than this Zeros-Poisson homology by definition of a conformal block. And this is finite by, I think, on Cedra. And and then you find that Zhu's argument applies without any changes. So this is a really direct consequence of result of, I think, of Cedra and argument of Zhu. Okay. Any questions so far?
Yes, Tomoyuki, I have a question. Can you hear me?
Yeah.
Is there any relation between the order of nilpotency of the conformal vector in RV and the dimension of simple ordering representations?
Cannot hear.
Is there a relation between the order of nilpotency of the conformal vector in RV and the dimension of the space of simple ordinary representations? In some cases there is. For example, if you take Virasoro minimal models, there is a simple relation. The order of nilpotency grows with the number of representations, I think. But I don't know if it's true in general.
So this order basically gives the order of this modular linear difference.
Not quite.
Not quite.
Right, as you know, there are cases where the recursion relation fails and you have to go to higher order.
No, I don't know the exact correspondence.
If I can comment, I think there are known cases in C2 cofinite vertex algebras where the C2 algebra has different dimension than the Zhu algebra. Yeah, indeed, Terry found examples of this.
So if you consider E8 level 1, C2 algebra is dimension 2. It is greater than 1, but much bigger than 1. But there's only one simple module. So this kind of correspondence, I think it's quite subtle. But there are cases when this number equals, for example, not classical types. So I don't really know what's going on here. Any more question? Okay. So I make one more remark. So one can also show if vertex algebras quasi-Ds, then its associated gradient is isomorphic to the so-called arc space of associated variety or the infinite jet scheme as topological spaces. I'm not claiming the isomorphic as scheme, but as a variety. It's isomorphic. So you can consider quasi-Lie vertex operator algebra as a quantization of arc space of the associated variety in a weak sense. Okay, so far I haven't given any example. So let me give some example. So let's do the favorite example, which is affine Katsumuri algebra. So let G be a simple Lie algebra, and let G hat be the corresponding affine Katsumuri algebra. Katsumuri. And then you can consider corresponding universal affine vertex algebra. If you fix a level, you can consider induced representation of this Lie algebra by from the one-dimensional representation of this parabolic subalgebra on which GT acts as 0 and the central element acts as this constant K. Then this has a natural structure of vertex algebra and called universal affine vertex algebra associated with G at level K. And so this is a vertex algebra. So you can talk about a representation of this vertex algebra. And the representation of this vertex algebra is nothing but the smooth G hat module of level K. So smooth means that the X tensor Tn act as 0 or if n is sufficiently large. So one way to think this vertex algebra is think as a enveloping algebra of the affine Katsumuri because representation theory is the same. And for this, Zudu-Schütz algebra is very easy to describe. So this is just a quotient space of this representation by this subspace. And because this is T2 minus 2 G T inverse VKG. Because this is isomorphic to enveloping algebra of T inverse G T inverse. And we forget anything which has power less than, so this one. So we have a surjection from bijection isomorphism of vector space from with symmetric algebra of G, which sends these monomial to the image of this vector. So this is isomorphism of vector space, but you can show that this is also an isomorphism of commutative ring, and it also isomorphism Poisson algebra if you identify this space as a function on the dual of G. So this is naturally a Poisson algebra where Poisson structure is given by a Kirchhoff constant Poisson bracket, which is just a bracket comes from Lie bracket of G. So, so this means that the associate variety or associate scheme is nothing but the dual of G star. But this is never this or never quasi-this. But you can make this universal affine vertex algebra smaller. So this is never not. Okay, so let's take a simple quotient of this induced representation. So this is unique, simple, graded quotient of VKG, then so this has a structure of vertex algebra. So it inherits vertex algebra structure from VKG and called simple affine vertex algebra. And for this one, the algebra has the same description. It's a quotient. It's just a quotient of this module by this subspace. And there's obviously a quotient of R of VKG, which is identified with a function on G star. So the associated variety of this simple quotient is a sub-variety of G star, which is a G invariant and point. So this is exactly the same in the case of primitive ideal of UG, but the difference is that if K is generic, then this induced module is already simple. So associated variety equal to the whole space. So it's not necessarily contained in the nilpotent cone of G. Q, rational number. And actually, one can show its converse. Maybe, yeah. Maybe I don't have time, so let's skip this. So, but another extreme is a case when this is this. So this is done by Frenkel Zhu and Don and Mason. The statement is this, that the LKG is least, which means that the associated variety is a point if and only if LKG is integrable as a representation of affine Katsumudi algebra. So this direction was shown by Frenkel Zhu for Z. So this direction is much more difficult. Yeah, this direction is much more difficult, as shown by Dawn. So in other words, these conditions characterize integrability for the affine Katsumudi algebra. So the least condition generalize integrability condition to arbitrary vertex algebra. So this is somehow natural condition for the natural finiteness condition. Now, so this is the case for these. Now, what about the case for the quasi-Lees? Now, the symplectic leaves of in G star are just coadjoint orbits. Joint orbits in G star, which identify with G, because Poisson structure comes from the Lie algebra structure of G. So from this, it's not difficult to see that this one is quasi-Lees if and only if the associated variety is contained in the null con of G. So this is a set of elements of G, which if we identify G star with G, set of nilpotent elements. And so this direction is obvious because there are only finite remaining nilpotent orbits in G, but another direction is not difficult to see either. So the question is when this happens. And we know that when LKG is integral, the associated variety is just a point. So we want to look for more general representation. And there is a candidate for such a representation. So integral representation of affine Katsumudi algebra are contained in the set of so-called Katz-Wakimoto admissible representation. Which still lies in the category O. So we know that the integral representation are very nice. It has complete reducibility. And the character modular invariant. But this Katz-Wakimoto admissible representation have the same property. But it's much bigger. And it's not least because of the theorem of Zhu and Don and Mason. So it's natural to ask, to expect that the associated variety of Katz-Wakimoto admissible representation should have a nice structure. And this is indeed the case. But before that, let me explain that this is admissible if and only if this. So this only depends on the level. So it's a condition on the level. So Check is a dual Coxeter number. So shifted level is a positive rational number. Where P and Q are some non-negative positive integer, mutually prime. And P is not so small, so it's a bit technical, but so H is a Coxeter number, and R check is a Lacing number, so it's 1 or 2 or 3, 1 for ADE, and 2 for BCF, and 3 for G2. And yeah, so let me state the statement. And statement is the theorem so if this is Katsuwa-Kimoto admissible, then you can describe, so it's in general, this is very difficult to describe because it's a quotient space of big infinite dimensional algebra by some infinite dimensional vector space. But for this, you can describe its associated variety explicitly, and it's quite simple. So it consists of elements such that add to x to q equals to 0, where q is a denominator of k as there, which is obviously contained in the nilpotent cone. And so this is a case when R check and Q are mutually prime. And for other case, we just replace this adjoint representation by irreducible representation with highest weight theta s, where theta s is the highest short root. Where theta s is the highest short root, and pi of theta s is the irreducible representation of G with highest weight theta s. So this statement in particular says that this admissible representation of quasi-series. And moreover, you can show, or in most cases it's been known that this variety actually irreducible. So there's some nilpotent orbit whose closure is exactly this variety. So. It's a very good question, and the answer is no. It's false. So I have shown that the admissible affine vertex algebra quasi-series, and so once Feldin and Frenkel conjecture that this property characterize admissibility, but the conjecture was false. Yeah, so I should remark that there exist quasi-Lie LKG outside admissible representation. So this was discovered by myself and Moreau. And also, Riva is going to explain about this next week, I think, where he is. So I finish with connection with 4D theory. So these are quasi-Lies. So the question is whether they come from 4D theory, and it's known by this physicist. So this admissible representation is come from 4D theory, actually from some Agrias Douglas theory. So which is some special case of 4D theory. If LKG is boundary admissible. And this boundary means that the numerator P is as small as possible. And actually, these quasi-Lies LKG outside admissible representation that we found also come from 4D theory. I'll explain about this maybe later. So maybe I should stop here.
Okay, are there any questions?
At the beginning, you gave the motivation with the X branch, and you said that the X branch are hypercolor. Is it the case for any associated variety? I don't know exactly the definition of hypercolor.
Associated variety in general are only Poisson variety. And so it's not symplectic. Of course, it doesn't have hypercolor structure in general. So the VOA coming from 4D has has special properties of the associated variety hypercolor cone. So in general, the question is no. Yeah.
Okay, thank you.
Hello. So going between the VOA and its associated variety, it seems like I can take vertex ideals and turn them into like sub-varieties maybe. Do you know how much it's possible to go the other way?
You're talking about quantization problem.
Yeah, I guess. Yeah. But, well, it doesn't have to be... Yeah, I guess I'm asking, like, do you know what ideals of RV I could, like, lift to... I guess, vertex ideals.
So if you don't impose anything, you can always quantize because you can always take corresponding arc space, and the coordinate ring of arc space is a commutative vertex algebra. But this is a boring example because it's a commutative. And if you impose simplicity, the problem becomes very difficult. And so it's an important problem, but I don't think people has worked out when you can quantize. And there's a subtlety about beam rastri conjecture. So the conjecture says Higgs branch is isomorphic to the associated variety. But the RV, so Higgs branch is a spectrum of some chiral ring, which is reduced ring. But RV is mostly not reduced. So so there's a subtlety in this conjecture. So maybe if I have time, I'll explain what is expected, but I'm not sure.
Right. Thank you.
Yeah, this is working. Yes, I think it's pretty much related to that question. Do you have any connection between this boundary admissible case? So this dichotomy between being boundary admissible and being just inside of the admissible set, and that one that you found there, and this condition of being classically free?
I think these are classically free.
Yeah, so we conjecture that too, but is there any? Is there any content to that conjecture in relation to this coming from physics, or?
I don't know.
Yes, can I answer that? May I answer that?
Yeah, of course.
So we would venture to conjecture that the BOAs that come from four-dimensional physics are all classically free. Oh. We have checked that in several examples.
Oh, so can you tell me what are these examples? Because already, so I've tried very, very hard to prove that boundary admissible for SL2 is classically free, and I cannot.
Oh, well, I'm not in the business of proving anything.
Oh, I see. Okay, yeah. So I've conjectured this too for affine algebras, but even for SL2, I do not know how to prove it. But you think so? So physics would say that these algebras, boundary admissible at affine algebra, should be classically free.
Honestly, it's just an observation that comes from looking at a few examples. So it's calling it a conjecture, but might be presumptuous. But it seems that it should be true. So as you know, there are all these examples of Argyres-Douglas theories that are lists, and rather remarkably, all of those that come from physics are classically free. And so there has to be the natural expectation is that this is a more general property. Now, one piece of intuition, which is probably related to this boundary admissible story, if you do the S reduction of the boundary admissible cases, if you do by the principal embedding, you end up in W algebras, which are I think believed to be classically free. Certainly, that's true for the Virasoro case. So that's to the extent that the S reduction, is compatible with this.
Yeah. So, but that's the reason why we know that the ones that are admissible and are not boundary admissible, those guys, we know they are not classically free because of this argument that we know it on the W algebra side.
Right.
But you're saying that you have examples that are classically free. In that statement, is it also a physics statement, or is it a mathematical statement that you have examples of classically free algebras? For me, it's very hard to find examples of this.
I wish I had a stronger physics intuition. I think at the end of the day, this must be related to the fact that four-dimensional theory has an additional structure which has not quite yet been incorporated in this mathematical discussion, which is four-dimensional unitarity. So as Tomoyuki emphasized, the two-dimensional theories are not unitary. Nevertheless, they do arise from a four-dimensional unitary theory. And so you have to be able to characterize in the 2D sense the properties that correspond to the 4D theory being unitary. So I will make some remarks perhaps next week in my talk.
Okay, thank you.
But yes, it's all experimental science as far as I'm concerned. We look at examples and make some plausibility checks. And then, of course, the other thing that it's usually true in theoretical physics is that the nicest expectation, which is not obviously wrong, is true. And so, that often leads to useful conjectures.
Okay. Are there any other questions? Let me just look on the Zoom as well. I think not. Okay, so let's thank Tomoyuki again.